So you would start making antibodies against that antibody. And then the next time you have to take it, you would have anaphylactic to do that immune complex formation, and you would have some even worse damage. And so there's ways to get around that. Let's get rid of the effector part of the molecule, like with these FAD22s. And there's been some other things done that you might hear about later in drug therapy. Chimeric antibodies that are part mouse, part human. Some that are humanized, where it's even less is shared. And then the idea is you can make antibodies in mice much easier to TNF. You can inject them with human TNF, and then make an antibody that recognizes human TNF, and you can isolate it, and you can make hybridomas, which make just buttloads of this antibody that is specific to TNF. But it's mouse, and it's not going to be very useful in the human unless you do something to it. And so that's what some of these new drug therapies are doing, is developing antibodies specific for something you want to neutralize, but getting rid of the effector part of the molecule so it doesn't cause the additional deleterious effects. Okay, hinge region, as I mentioned, it just gives it a little more flexibility. You can see here that here you got you can get these antigens binding together. You can form what are looking like immune complexes, and we'll talk about these a little bit later when we talk about precipitation and the precipitin reaction. Because antibodies are multivalent, which means they can bind two antigens at the same time. If you have multivalent antigen, then you can start forming these lattice structures and these immune complexes. Bacterial cell wall polysaccharides are one of the things that you would find this with. And they're all over the cell wall of the bacteria. And if you have these multivalent antibodies, they can bind, both of them can be bound instead of just one of them. And as we'll see a little bit later when we talk about one in particular, IgM, it is 5 of these Y-shaped molecules bound together by the Fc portion. And then so they have a valency of 10. They can bind 10 of these antigens by one molecule. And then they can fix complement and do some other cool stuff. All right, heavy chain, 5 isotopes that come. And of course they're great, what we call IgM, IgD, IgG, IgA, and IgE. There are 2 isotypes of the light chain, kappa and lambda. And you will only have one of the heavy type and one of the light type to form the 4-chain molecule. So when we talk about the mu chain, we're talking about the heavy chain that would encode for IgM. The ones that are most important as a clinician is going to be IgG, because it's the one that's doing a lot. It's the one that really comes out of a vaccination. You start by making M, and then you get, as the immune response gets better, you switch to some of these others. G would be one that you would think of the most as being important in immune responses. A is found on mucosal surfaces. It's specialized. E, you already know about. It goes and binds to mast cells, and unless you're around a lot of parasites that you're engulfing, all it does is cause you allergic reactions. Kappa and lambda we don't worry about. It's just two different versions that gives a little more variability to the process. So here's what it looks like. If you were to look at these things as the Y-shaped molecule, what you'll notice is that they look very similar, except IgM and IgE look like they have one more blue box on them, and they do. They have a little bit longer Fc portion than the others do. You see IgD there, IgA, and we'll see how these things interact as we go through it. So there happens to also be subclasses. There's only one IgM, only one IgD, one IgE. But there are 2 versions of IgA. IgA1, IgA2, and there were 4 versions of IgG. 1, 2, 3, 4. And they have slightly different effectors. If you take the secreted form of IgM and you add this protein called the J chain, it helps them form this pentamer. And so here we have 5 IgM molecules, so a valency of 10. It will bind 10 of the same identical item. Just always remember, that heavy chain is identical. All 10 of them that are on there are identical in amino acid sequence. All of the light chains are identical in amino acid sequence. So they recognize 10 of the exact same antigen. They can also form hexamers, but at a much lower level. Here's the secreted form of IgA. I told you it's a little bit different. There's a different J chain that interacts and causes them to form these two together. And then there's also a molecule called the secretory piece that these secretory IgA molecules bind to epithelial cells and can be transported across into the mucosal surfaces. The lumen of the gut is one of the things that comes into mind. So you have an antibody that's produced by a plasma cell, and it can cross through the epithelial cells to get to the side, the mucosal side, and it somewhat sticks kind of on the extracellular side of mucosal surfaces and is important in pathogens that come in. At least that's what we think. This is just some characteristics I don't want you to get hung up on. I just want you to visualize something. And the main thing to see here is IgM is a lot bigger because there's 5 of them hooked together. But if you look at the third thing down, it says serum level. And you can kind of get some sense of how much these things are in the serum. But you look at the farthest one down there, 5 times 10 to the negative, what is it, 5. Very low concentration in the serum. The reason why is because as soon as it's made, it almost immediately gets bound by a mast cell. So there's very little free IgE floating around the serum. It's all bound to the mast cell to be involved in expulsion of parasites or allergies. Okay, these are some of the characteristics. Again, I'm not expecting you to know what IgG1 is. I do have some things that I do have some expectation. I do expect you to know that IgM is the first one made, which we'll get into in later lectures. I expect you to know IgA is important in the mucosal surfaces. IgE is involved in allergic reactions and binding to mast cells and eosinophils. And then IgGs are going to be the ones that are most important in most of the immune responses that we're thinking about. So you go, well, what about IgD? Well, it actually doesn't play much of a role in immunity except when the B cell is going through development. So we don't worry about IgD. It's more it's just kind of a leftover from the development process. Oh, and then I will say, transport across epithelium, secretory IgA, we've already talked about that. It can move across the epithelium and the mucosal surfaces. And then if you look at transport across placenta, not really, none of them do it except IgG. And that will become important later if we get the chance to talk about blue babies, Coombs disease, the Coombs reaction, those kind of things, what's going on there. The mother is making the antibodies, and the same antibodies that she's making is getting into the blood and the serum of the fetus. Not the B cells, not the plasma cells. Just the antibodies crossing over and getting in there, and it's the IgGs. When the baby is born, then the baby is more susceptible to mucosal tissues, still has a high level, has the exact same level of IgG from the mother that the mother has, at least for a little while until it goes away. But the breast milk has that secretory IgA in it, and so that augments the mucosal defense for the baby until it starts developing its own immune responses. Domain structure, and now we get into the biochemistry part. And this is where I'm not getting kind of, yeah.
Sorry. Is there, so since you were talking about how that breast milk is how they get the IgA or whatever, what happens if, like, for some odd reason they can't get breast milk?
Then they're not getting that IgA from that parent, from that mother.
Do you have to supplement this?
You can supplement it, you can do whatever you need to, and the baby may be fine.
Okay.
I mean, hygiene, the way we do things now, they're probably going to be fine. But that wasn't the case during evolution.
Yeah.
That IgA was necessary for the baby to have those mucosal surfaces protected. We have antibiotics now. So. Yes?
So just to clarify, IgG is through the placenta, IgA is through the breast.
That is correct. Did you hear that? You said it perfectly. IgG goes through the placenta, IgA is in the breast milk.
That's why we like women to breastfeed for up to a year, because it takes the gut 1 year to develop enough maturity to not allow foreign proteins to enter. So why we think cow's milk may be setting off like type 1 diabetes. So, very good point.
Yes.
Very
Because
good
it takes
point.
a while. The babies don't have, the fetus doesn't have its own microflora. They have to start developing that once they're born. They pick up some of it if they're delivered naturally through the vaginal birth. They're picking up some of the microflora at that point, and then they're developing it over time. So they need something like that to supplement, unless you're in a place where there's lots of clinical help in case the baby gets sick. So, yeah.
So I think I saw in one of the videos, but like, are the IgGs that we receive through the placenta, are those just temporary?
Yeah.
Okay.
Yeah. So any protein is going to have a half-life. As it floats around, it's eventually going to be picked up by something, there's filters and cells that pick up these proteins after a while and degrade them. So it's only going to last a certain time. I don't remember the half-life, but I will say, let me go back. I think it's a different slide. Oh, half-life and serum. So if you look, IgG1, 21 days half-life. So after 21 days, you have half as much. And after 21 days, you have half as much left. So the IgG is sticking around quite a while, but it's not going to be that long before the child needs to start producing their own immunity. Okay, variable domain. Like I said, I'm not going to get into this too much. You're going to see some really cool pictures because as nerdy scientists, we like to show beta pleated sheets and alpha helices and all that kind of stuff because it looks really cool. But the antibodies are made up of certain domains. And it's actually made up of the immunoglobulin superfamily of genes. And so they were first identified in immunoglobulins, but we're finding them in lots of proteins. They have a very useful structure and function. So we have one variable domain, sorry, on the heavy chain, one variable domain, and in all the pictures that we looked at, it's been like the red one. And then 3 or 4 constant domains. Remember, IgE and IgM have one more domain, one more of those things sticking down there. So that's typically been the blue thing. Light chain has one of each, one variable and one there. And this just kind of shows you that. If we just focus on the right side, you see those yellow domains, CH3, CH2, that would be the heavy chain, and it's showing you CH1, CH2, and then it goes up to CH1 is a little higher up, and then we have the VH would be right over there to the right. It actually go over to the blue because I guess that's what they're labeling them. So you have 3 constant domains and 1 variable domain on that molecule. The light chains just have 1 of each, and that's all we really need to look, except to get to see how the structures look when they really get down and look at them. This is the part that I want you to really hammer in on. And this is showing you the structure of a light chain. And so the constant domain is down there on the end, and it's just happens to be that's where the C-terminus is. So N-terminus is over here, and the variable domain, the C-terminus is in the constant domain. And this stuff over here, the yellow and whatever color that is there, green, that's not going to change a whole lot in all of the kappa light chains or in the lambda light chains. It's going to be very small differences, really. The big differences are going to be over here. And what I want you to see are these loops sticking out. One loop is listed, but you can see, it looks like there's 4 loops, but there's really going to be 3 main loops that are sticking out of that one part. Those are the parts that interact with the antigen. That's where the amino acid sequences are going to change from one antibody molecule to the next. And we're going to talk about that in just a minute because it helps you visualize how we can have so many different specificities with this molecule that looks so much alike. All right. V regions of the heavy and light chains contain 3 areas of hypervariability. This corresponds to the 3 loops I just told you. We call them complementarity determinants. These are 1, 2, and 3. And they are flanked by these framework regions which are constant that are important in structural integrity of the molecule. The variability in those loops or those CDRs is what gives us the diversity of the immunoglobulin specificity. See what's next before I Here's my visual. Okay, I'm just gonna go on to this next thing, and we're gonna do something. This is showing you the amino acid sequence, and the variability in the amino acids of a particular, this is a light chain, B region area. And what you can see is that for the most part, the yellow regions, there's some variability, but not much. So what they've done is they've sequenced a lot of variable regions from antibodies, and they find that there's some variability in these yellow parts. Those are called the framework regions. But there's a higher variability in these red areas, hypervariable 1, 2, and 3. Those correspond to the CDRs. That's where the loops form, and if you were to look back at the structure, the loops come up. That's where you see a lot of variability in amino acid sequence. Same thing's going on. Well, this is just showing you where those are. So those 3 red things are going to be the CDR1, CDR2, and CDR3 of the antigen binding site on the light chain. The same thing is taking place in the heavy chain. I think, is that the next time? Yeah. So we have, and this is, it's even more prominent here, in that if you look at the heavy chain variable region 1A, the amino acid sequences in those 3 areas that correspond to the loops that are sticking out, very highly variable. And that's going to be the part that that's the antigen. What I want you to consider is this. So if you have your left hand, you have, take 3 of your fingers and 2 of your fingers and your thumb. Those are the 3 CDRs. And the right hand, so this is the light chain. This is the heavy chain. And you have 3 CDRs there too. And you hook them together, and now you've got 6 pieces of the protein that are interacting, and all 6 of those are highly variable. And so it could be something like that, it could be here, it could be that. These are going to change depending on what the amino acid sequences are, and you change what binds in there. So that's the variability that is part of, that makes the antibody molecule specific for an antigen and specific for only one antigen. Yeah.
Oh, okay.
Yeah. Well,
I was wondering if they bind like 6 different things, or they're all very
only
close
if
to
they're
binding
very
one?
close. Only if they're very close in structure. They tend to bind things that are they're very specific, and the affinity is going to get tighter if the interactions between the 6 loops are better.
Okay.
So I'm glad you brought that, because what's going to happen here is, say this is the antibody that you made against antigen A, and antigen A fits in there very tight, high affinity. But when you go through what we're going to call affinity maturation, we'll talk about it a little later, there are hot spots for mutation in these 6 areas. They mutate much higher than normal DNA does. When a cell goes through proliferation, when DNA is replicated, there are mutations in it. And you could just have one amino acid change that just does that right there, and now it's a higher affinity. So that antibody is even better than the antibody before. Maybe it got worse. Well, if it's worse, it's less affinity, it won't get selected. It'll eventually go away unless it binds to an antigen better. So it turns out that the first B cells we make are called B1 cells. They have a low affinity. They bind to multiple antigens, but they're all polysaccharides and not very good. As we develop these B2 conventional B cells, they are specific for one antigen or a very highly related set of antigens, but the more the immunization goes, the more tighter and higher affinity it is, and the more specific it becomes, to where it's just very, only one type of antigen to fit in there.
Did you say the hotspots for mutations are in the CDRs or
They
just?
are.
Okay, they are.
They are. Hotspots for mutation, when we talk about that a little bit later, I think that's later this morning, that's where, and I do not know the process or the mechanism for that, but it is very clear that there can be mutations in other parts of this, in the blue areas, but most of them are going to be in those 3 red areas that would correspond to the loops of the CDRs.
So do the mutations occur when those B cells are getting better? You talked about the B1 and the B2, so is it within the B cell each time another generation?
Let's not call it, let's go back a different way. You're right, but I don't like the way you say it, because
Okay.
it's random. The B cells are not getting better. What's happening is the B cells are proliferating. And when they proliferate, for some reason, those spots are hot spots for mutation. And during the DNA replication process, you know that there's high fidelity in DNA replication. The machinery does a fantastic job of making sure we don't have mutations. Not so in this case. We get mutations in these areas. And what's going to happen is, say you start with one B cell clone and it's interacting with its antigen and it starts proliferating. Now you have 2, you have 4, whatever. Every time that there's a replication of the DNA, you have this opportunity to introduce a mutation. Now in the end, what's going to happen is, if the antibody that you made mutated and it's not as good, it's going to take a lot more antigen to stimulate it, so it's not a good B cell. It won't make it. It won't be activated. The other B cells that got better from the mutation, antibody titer binding, they respond to lower levels of antigen. It's all about the concentration of the antigen. The lower the concentration of the antigen, and you know this from receptor ligand interactions, I know that Dr. Latassi talked about this already. The lower the concentration of the ligand for the receptor, the more specific it has to be to work. And so the higher the affinity that the receptor has for its ligand, then the lower levels you can have and still get a response. And so the higher affinity B cells are going to respond, the lower affinity B cells are not. Does that make sense? Okay. All right, this is just a goofy picture, but what it says is, just like I showed you with the 6 CDRs, they're changing. You've got lots of different antigens. Some of them are going to be like a pocket. Some of them are going to be more extended like this groove shape. Some of them are going to be even bigger, like the polysaccharides. So the region that the 6 CDRs, that little pocket that they form, may actually be the opposite of a pocket. The antigen may stick down in there, the antibody may stick up into the antigen. It's all about the interactions between the amino acids on the 2 chains of the antibody molecule and whatever the protein is. It could be a polysaccharide, it could be a protein, it could be a lipid, it could be DNA. We actually we can make antibodies to DNA, but you just don't see them being used except in autoimmune diseases when DNA gets out from damaged cells. So lots of different types of antigens. We have lots of different types of antibodies that can respond to them in different ways. This is just showing you, and I wish they'd use a different color, but what this is showing you, if you look at the thing on the bottom there, it's the exact same protein antigen. Those are supposed to basically be amino acid residues forming this globular structure. You can have multiple epitopes or antigen determinants, the part that actually is recognized by the antibody molecule. Multiple epitopes on the same antigen molecule, same protein. So an antibody on the left panel is recognizing this linear epitope, and don't worry about those. It's showing you 3 amino acids or three somethings. It doesn't matter. Just it's recognizing a linear part of one side of the antigen. The other one is recognizing more of a globular, more distant type of epitope. And in fact, that's what you do. When antigens come in, some of the things that you're exposed to are very large. The larger they are, the more immunogenic they are. So you're going to make antibodies to lots of different things on the same antigen. So you have antibodies that are going to be high affinity for this part, low affinity for that part, blah, blah, blah. You're going to have antibodies to lots of different things as long as they have some immunogenic property. Now you're sitting there going, well, how do you have all these different antibodies? Well, we're going to get into that. But it is a random process, and it is going on in your body right now. And it starts going on early on in your life. You start making these B cells that have all these different millions of specificities. Valency. And so the Y-shaped antibody molecule has 2. Secretary IgA has 4. IgM has 10. It can bind to 10 different antigens. That's valency. And so when you have multivalent antigens, you can have things like this going on, where you have 4 different antibodies binding because there's 4 different antigens on epitopes on that, whatever that antigen is. And then you can have the antibody molecule binding to both arms are binding to the antigen because it has a repeat epitope. That's where IgM comes in, that pentameric form. It's going to really bind tightly with high affinity. Well, no, I'm not going to say high affinity. It's going to bind tightly, not because it has high affinity, but because it has 10 things to hold on to. We're holding on to it in 10 different ways. Yes?
So if it's a different epitope, it's gonna only bind with one of the arms, but if it's repeated, it'll bind with both?
That is right.
Okay.
If you only have one of that epitope, only one arm is going to bind to it, and that's not the best.
Okay.
That's not always going to be
So you prefer to
enough.
have repeated?
Yeah, and in fact, let's see, yeah, that kind of brings up, yeah, repeated epitopes are going to be, you're going to have stronger binding even if you have low affinity antibodies. You can still have good binding of antibody so long as it's a high affinity antibody, if you only have one epitope on there. And then, so this is valency and binding. We have avidity versus affinity. So this first part, association, dissociation. This is that affinity thing that I said, Dr. Latassi talks about ligand-receptor interaction, on off. Depending on how tightly something binds, they bind and release. The higher affinity, the longer it takes to release. So we have association and dissociation that is affinity, but if you have multiple interactions, like we have this related thing here, it's going to take more for the antibody to release from it because it's binding twice. So one can come off, the other one's still attached, so you're still attached. And then this one can come off and you're completely dissociated, but maybe while this one's coming off, this one's binding back on. Multivalency, even in a low affinity antibody, allows it to stay attached longer and better than if it just was binding with one epitope. Let's talk about antigens themselves. The size matters. Large molecules, especially proteins, if we're talking about in this case, that you have better immunogenicity. So how do we get an antibody response to a very small protein? You attach it to something else. You attach it to something big. And what they're doing a lot now, not just with small proteins, but with other things like polysaccharides, they're attaching them to the deactivated tetanus toxin that you're getting in your DPT vaccine. So not only are you getting a boost from the tetanus toxin, but because this smaller molecule is attached, as it happened, then it is also stimulating the immune response. Small one's not good. Dose, you want to give them an intermediate. You give them a high dose, tolerance. You can think of it like this. If there's a whole lot of antigen in here, the immune system might think it's safe, and so we're not going to respond. But that's not really true. High dose, bad. Low dose, you just don't have enough to stimulate the response. I already told you about tetanus toxin. It will kill you before it gets in high enough concentrations to stimulate an immune response. That's why it's critical that you get those vaccinations. Subcutaneous is much better than intravenous. A lot of what we do is intramuscular, which is fine. A particulate is better than a soluble type of antigen. And you want the proteins to be very different than your own self molecules. This is where you hear people talking about vaccines. They start saying, well, this so-and-so vaccine looks too much like this self-protein, and therefore you can break tolerance to a self-antigen, and then you've got a problem. And there was a big stink about some vaccines and multiple sclerosis years ago, but we're not going to get into that. That's more politics than it is science. So that's immunogenicity. These are adjuvants. You're going to hear something this afternoon called co-stimulation. It has to do with getting T cells stimulated. And the way to get T cells stimulated is they have to have more than one signal. The antigen and MHC and the T cell receptor, CD4 is binding to class 2 and antigen. CD8 binding to class 1 and antigen. That's signal 1, but you need the second one when it's a non-T cell. That's that co-stimulation. Adjuvants can provide that because what they do is they soup up the antigen presenting cell and get that. What you guys get, as far as I know right now, all we're still doing is the alum. Do you know anything else, Dr. Latassi?
Say it again.
Is it just alum that we're using, or are we even using alum much in our vaccinations in humans?
Oh, I know we use a lot of adjuvants. I don't know exactly what they are, but that's important for
You
them to
certainly
remember
can't
for
use-
vaccines.
The incomplete flowings is just an oil and water emulsion, and it's basically mayonnaise. If you ever taken
Ugh.
oil and water and smashed it together, it becomes mayonnaise. And this is what we eat as mice with a lot. But the complete flowings adjuvant, we add dried microbacteria in there. And it's a fabulous adjuvant for getting good immune responses going, but you can't use them in humans. They only let us use them in some laboratory animals now. You have to get special permission to use some of these adjuvants. But they're coming up with some new ones that might be of use in the future. All right, we're going to quickly talk about some of the interactions that take place. Precipitation is a term for when you have a soluble type antigen. It could be fairly small, but it's multivalent antigen, multivalent antibodies that are recognizing it, and they start binding to each other. And if there's a lot of antibody in there, then you get this zone called antibody excess, where the complexes between antibodies and antigens are not very big. So you're in the amount of antibody that might precipitate out, which is called, when you get these big immune complexes formed, they get too big to be soluble in the fluid. And so they precipitate out, and that's why it's called precipitation, or the precipitin reaction. If you have too much antigen, you have the same thing going on the other way, but it's the opposite. You have antigen is bound to both of one antibody, and you don't get the complex formation. But when you get in this equivalence zone, you start forming these large immune complexes. Now, why do you care about that? Well, because if you get immune complexes forming, what happens is they start depositing on vessel walls. And then it calls in other cells and inflammatory cells, and the immune complexes can start causing all kinds of pathological damage, glomerulonephritis and kidney damage. These immune complexes can be really bad for you. And this is one of the things that happens when they would give horse antiserum for a rattlesnake bite to a person, and then they give it to them again. But one thing, you have to have it in such a way, you have the antibody in excess when you give the horse antiserum, so that it sops up the antigen without forming huge immune complexes. But now you've got the added thing where now you're making antibodies against the horse, and at some point, there's an equivalent zone, immune complexes start forming, and it just screws you up. There are, I'm from a town where we hunted rattlesnakes, and people would try to raise the rattlesnakes, and they would get bit. Well, the first couple of times they get bit, it's bad. But they eventually start getting so much antibody, they develop antibody themselves, that they get this big slug of antigen in there, and you've got this antibody rushing in there, the immune complex is forming, and the hand becomes huge, swollen, starts turning black and necrotic in a matter of minutes to hours. And basically, it's amputation. There's not a whole lot you can do at that point. So these immune complexes, they're not so great if you get into neutralization zone. Then there's agglutination, and this is an example of hemagglutination. So agglutination is when you have a particle, multivalent particle, that antibodies bind to, and you can form. They can agglutinate. The particles can form a lattice that agglutinates out. And this is showing you what's going on in blood typing, okay? And this kid's kind of ugly because it's antibodies responding to polysaccharides. They're not good antibodies because they're too polysaccharides, and you don't need good T-cell help against polysaccharides. But this kind of gets at, okay, if we look at the top, red blood cells from individuals of type O, you don't have an A antigen or a B antigen on your surface. And it's just showing you some of the carbohydrate structures. So the thing is that we really need to go into how B cells are formed before you really grasp all this stuff. But this is getting into, because you don't have an A antigen and a B antigen on your red blood cells, you can have antibodies to A and B in your system. Where would you get them? Bacteria in your gut actually have some of these same polysaccharides, and you can develop antibodies against them. But if you're A type, you have the A antigen on your surface of your red blood cells. We got rid of those B cells when they were being made. So you don't have anti-A antibodies, you only have anti-B antibodies. And we'll get into that a little bit later, but I wanted to bring this up now, and I'll probably bring it up a little bit later, and we'll talk about what's going on here, because the last thing that I was going to talk about was the Coombs test. I'm going to hold off on that too. I want to come back to these a little bit later and talk about them in a little bit more detail. What I want to do now is, I want to break now because we're going to start immunoguarding diversity, and we're going to spend an hour on it before we go to lunch. So I'm going to get started right back again at 11 o'clock, and we're going to talk about the development of these antibody molecules, how it happens.
Is your computer okay?
Yeah, I don't know, the mouse isn't working, but I could return it and go get a new one, so I think that's what I'm gonna do.
Oh, goodness. So sorry.
It's touchscreen, but I need the keyboard too, so I'm
Yeah.
probably gonna go after class today.
Oh, gosh.
Good thing there's that 30-day return period.
Yeah.
Well, you can't
Gonna get warranty for sure this time.
And then there's four types. The first one is the last one, number 4, is the late type toxicity. It's T-cell. And 2 and 3, 2 more 3, have to do with immune complex. And she'll go into that. This is just want you to understand that the antibodies, because of the way they're designed, can't form these immune complexes. It forms inside your body, not so
Hey, do they have a baby yet?
No. I should have brought that.